Welcome everybody to the next session, Topological Data Analysis. I'm happy to see that there are so many great topology submissions that really made it in the main conference. We have 6 very interesting talks ahead of us. So the first talk will be given by Yuxiao Li, and she will talk about an efficient parallel algorithm for correcting Morse-Smale segmentations in arrow-bound lossy compressors. So, Yuxiao, could you share your screen? And the floor is yours.
Okay. Can you see my screen now?
Yes.
Okay. Thanks for your introduction, and good morning, everyone. My name is Yuxiao Li, a PhD student from the Ohio State University, and today I'm going to present our work titled MSC, an efficient parallel algorithm for correcting Morse-Smale segmentations in arrow-bound lossy compressors. And so first of all, why we need to use the arrow-bound lossy compressor? This is because the volume of scientific data is very large these days, and scientific data is actually difficult to compress due to its high precision requirements and complex structures. And therefore, one could sacrifice certain data quality to reduce the data. And one solution is the arrow-bound lossy compressor, which could kind of achieve a high compression ratio by introducing controlled pointwise error into the decompressed data. And for example, SD3 and ZFP are two of the state-of-the-art lossy compressors these days. And the arrow-bound could kind of control how much quality can we sacrifice to reduce the data. Well, this is good for control the data quality, but one question is whether it could preserve the topology in the data or not. And the answer is no. Today's arrow-bound lossy compression rarely consider preserving the topologies, which might kind of influence some applications analysis on the topological descriptors. For example, in figure A here, where a lower rate of false cases, which is actually the y-axis here, indicates a better preservation of a specific topology. And we need to crop down the arrow-bound to very low so that there is no false cases. And figure B and C shows the topology of the input data and the one in the lossy compressors decompressed data. Now we can see that the compressor would distort the topology to a very large extent. And existed topology preserving lossy compressors had considered preserving topologies like contour trees and precision diagrams in the scalar fields, and also the critical points in the vector fields. And as for our work, we're targeting a kind of completely different topological descriptor, which is the piecewise linear Morse-Smale segmentation, or PLMSS in short. So what is PLMSS? It actually consists of extrema, which we refer as critical points in the later context, and also the ascending and descending segmentation that divide the domain into monotonous segmentations, where each data point or vertex within the same segmentation is monotonous. Imagine that this figure here is a picture of different mountains and with a lot of different peaks and valleys. And for two people standing in the same segmentation, by following their speediest ascending or descending direction, which is actually the integral line, and they will reach to the same maxima and minima, which we call them as the label of each vertex in the later context. So actually the instruction of the MSS is highly depending on the comparison of the scalar value of each vertex with its neighbors. So even minor errors introduced by the lossy compressors would distort the MSS result. Therefore, our paper's target is to preserve the MSS so that each vertex label will be exactly the same as in the original data. And our main idea is that we're directly working on the decompressed data, and then we identify a subset of data points that need to be edited or modified to preserve the MSS. And generally speaking, the output of our algorithm is a set of edits in a kind of key value pair, which indicating the modified data points at index and their respective deltas. And there are three requirements for the preservation of the MSS. The first one is the preservation of the critical points. And after this, we need to preserve the minimum and maximum labels induced by the integral line of each vertex. And the last one is the preservation of global error bound, because we're going to modify the decompressed data. So we need to guarantee that the modified decompressed data is still bounded by the global error bound. And here is a simple illustration of our workflow. And our method is mainly during the compression process. That is when before things are down to disk, we could have access both of the original input data set and also the original decompressed data. And then we can extract the MSS of those two, and we compare them to extract the false cases. And if I detected false critical points, then we enter the C loops to fix them. And after the C loops, we need to check if there is any false labeled points. And we enter the R loops to fix them. And note that in both of the loops, we are going to modify the decompressed data. And any modification would kind of introduce new false cases. So we need to go back to the C loops to fix the newly introduced false critical points. And those two distinct loops will be executed iteratively during the iteration, and the whole process will only exist when the MSS is fully preserved. And at this point, we get a version of fixed decompressed data, and by making difference with the original decompressed data, we can get the edits, and then we compress it together with the compressed data as the output of our algorithm. And in the decompression process, we just apply the edits on the decompressed data to get the fixed one. And generally speaking, the fixed process mainly involves modifying the values of the vertex itself or its neighbors. And here I will use a simple example of our methodology on fixing a false positive max in the C loops. And the figure here where I is a false positive max, and the height of the balloon cylinder above each vertex represents its lower bound. And the height of the pink one represents its current value. And the semi-transparent cylinders correspond to the values of each vertex in the original data. So at first, I is an FP max, so we decrease the value of it, which might make J a new FP max. Then we decrease J. And unfortunately, I becomes a FP max again, then we decrease it again. And at this point, I's value is smaller than J's lower bound, which means no matter how much J decreases, its value will never be lower than I. So I will never become a new false positive maximum anymore. And then we call this situation as I has been fixed. And for more complicated cases and proof of convergence of our methodology, please refer to our paper. And we also use the parallelism to accelerate our workflow, as we need to repeatedly execute those 5 blocks during each iteration. And the serial processing is somewhat computationally expensive. For example, with a next dataset, running the entire workflow in the serial process takes several hours, but compressing the dataset only takes a few seconds. We evaluated the parallel performance on the next dataset, and for the end-to-end time, we achieved a speed up of 198. And the other components also achieved a different speed up. And other than this, one challenge is the read-write and the write-write conflict when multiple threads attempt to modify the data concurrently. And I will use one simple example on how the conflict for the task to fix false critical points. What we do is that we assign each thread to be responsible for fixing a false critical point, which might introduce write-write conflict if 2 threads is going to modify the same vertex value. And here is the example. The left one is the ground truth with colored circles represent the critical points. And the right one is the result of the decompressed data, where circles with red stroke indicates the false critical points, as it has a different type than it was in the original data. And in this case, thread 1 and thread 2 is going to modify the same vertex 21 with different delta, which is at 1 and at 2 here, where only one delta will really be applied, which might lead to inconsistencies in the result. Therefore, we use the atomic operation to only apply the deltas on the same vertex with the largest absolute value, that is added 2 here. And then we can get the deterministic result, also guarantee the convergence of our methodology. And here are some of the results of our method's ability to preserve MSS on datasets from combustion, where PLMSS could be used to identify flame structures. And figure A is the MSS of the original data, with spheres represent critical points, and figure B and C are the MSS of SZ3's decompressed data and ours, with spheres represents false critical points. And we can see that SZ3 would kind of distort the MSS a lot, where our method could fully preserve the PLMSS. And as for the limitation of our future work, our work could be optimized in various aspects. First, our method would introduce storage overhead as we need to store the edits, but we still delivers reasonable overall compression ratio with feature preservation, and when compared with the lossless compressors, because we could achieve a compression ratio that is larger than 2. And also, we would introduce computation overhead as we need to compute the MSS during each iteration, but our timings are still within the same order as the time to compress data with SZ3 and ZFP. And second is that our method can be extended to preserve the full MS complex by addressing the preservation of saddles and the saddle-saddle connectors. And this is also a direction of our future work. And I think that's all from me. Thank you for your listening, and I'm happy to take any questions you may have.
Thank you very much for this interesting talk. So far, there are no questions here on Slido, so I can ask you a few of my own questions. So at first, I was wondering, when I see kind of your decompressed data, there are so many critical points. Did you try out what happens if you would do a persistent simplification according to the error bound that is given, and see what the result would be in comparison to the original data?
Currently, we didn't try the simplification on the decompressed data yet, but I think this is a kind of future direction, because if you simplify the data set, and there will definitely be like less false critical points in the data set. Yeah, we're still working on this.
Yeah, in the meantime, there's also a question on Slido. So at first comment, very interesting work. Can you imagine a worst case input where the count of C and R loops would be very large?
I'm sorry. I imagine the worst case input of the C loops and R loops would be very large.
So I think what would be a really bad condition, so that you have a lot of overhead and maybe also a lot of overhead in storage and decompression time.
Yeah, if you have a very like large error bound, which means that there will be a lot of errors introduced into your data set, then there must be a lot of iterations for you to fix those or all of those false cases.
Okay. So there's another question. You mentioned about global error bounds in the beginning. Is the error in voxel values, critical point position, or MSC boundaries?
This is the error in the voxel values. That is the scalar value of each of the data points.
Okay. Thanks a lot again. I think we should move on to not fall behind schedule.
Okay, thank you.
Thank you. So the next presenter is Weiran Liu, and he's talking about fast comparative analysis of merge trees using locality-sensitive hashing.
Okay, all right. Thank you. So hello. My name is Weiran Liu, and from the University of Utah. So today we will explore the intersection between topological data analysis and locality-sensitive hashing. So scalar fields are everywhere. They arise from like scientific simulations or measurements. An example of a time-varying scalar field shown here coming from a simulation of the Red Sea. We use the velocity magnitude field here as the scalar field. To study the circulation dynamics of the Red Sea, we are interested in studying the similarities and differences between each time step. But we do not want to compare two scalar fields directly. Instead, we want to study their structural similarities and differences using topological descriptors, because topological descriptors capture essential features for comparative analysis and they are robust to noise. So the key idea is to define comparative measures between merge trees that summarize the underlying scalar fields. A number of comparative measures have been developed for merge trees and their variants, so such as edited distance and interleaving distance. However, many comparative measures do not scale well, even with polynomial algorithms. The issue of computational efficiency is especially important in studying time-varying scientific data and ensembles at scale. So we have turned to locality-sensitive hashing to address these questions of efficiency and scalability. So in particular, we compare our LSH-based similarity measures with edited distance and with geometric aware interleaving distance to show the capability of our method. Here's a highlight of our contributions. First, we proposed two new similarity measures based on the LSH called recursive mean hash and subpath signature. Second, our similarity measures closely resemble the results of existing comparative measures. And third, our LSH framework demonstrates the utility in various applications, such as chip matching, data summarization, and transition identification. And lastly, our methods achieve about 10 to 30 times speedup on moderate datasets and a very high speedup on large ensemble. So given a set of scalar fields, we generate our distance matrix in the following three steps: pre-processing, signature generation, and locality-sensitive hashing. We first simplify each scalar field with a small persistence threshold to remove noise. We then compute merge trees followed by label assignment. So now let's look at what is a merge tree and a label merge tree. So given a scalar field, a merge tree captures the connectivity of its sublevel sets. The critical points are colored by their types, so local minimum are in blue and saddles are in white and local maximum are in red. We use the label strategy from Yang to label the leaves of the merge tree, and then note that a node can have multiple labels. So now we have a set of label merge trees. We want to convert a merge tree structure into a LSH structure. So our new methods are based on a hashing technique called mean hash. So assume we have a set with 5 elements, A, B, C, D, E, which can be indexed from 1 to 5. Given 3 sets, S1, S2, and S3, we can represent them using a 0-1 encoding, such as S1 can be represented as 11100, and then S2 can be 01001, and so on. So then we generate k number of random permutations based on elements indexes. Set k equals 2, these permutations provide us 2 hash functions. For the first hash function, what mean hash does is to store the index of the first occurrence of 1 in that particular permutation for each of the set. Then we store the indexes of each set based on the first permutation, and so we have this 3, 2, 4 as a hash vector based on the first hash function. And similar for the second hash function, we again store the indexes of each set based on the second permutation. The signature matrix is formed by combining the indexes of these 2 hash functions. Each hash vector is of length 2, and then finally we obtain our signature matrix for S1, S2, and S3. So a recursive mean hash from merge tree uses k-mean hash repeatedly by following a bottom-up approach to compare the hierarchical data. We illustrate our method using an example of 2min hash. So first we apply 2min hash to each leaf node to get our hash vector. The same color reflects the hash value coming from the same hash function. Then reorganize the hash vectors that share the lowest common ancestor into two sets by taking the ith term from each 2min hash vector into the s set. Now hash values coming from the hash vector are in the same set. Then we move one level up by taking the two sets to their parent and then truncate the old leaf nodes. We recursively perform these steps until we reach the root node, and then we apply 2min hash again to get the final signature after concatenation. Subpath signature is another way to generate a signature for a merge tree. So given a labeled merge tree, we can identify the elements of a set of subpaths. We generate all subpaths starting from the root node and traverse down to collect them in a multiset. Here we set the subpath lengths to be 3. We first include a path containing 2 dummy nodes leading to the root node. This ensures that all subpaths would be of length 3. After adding these 2 dummy nodes, we collect all the subpaths of length 3 from the new root. And then we traverse down the tree until every node has been visited. We then apply 2min hash to the entire multiset of all subpaths. Each subpath is considered as one element in the set. We then get one signature for the merge tree, and finally such a signature is taken as the input for locality-sensitive hashing. Now let's see how to turn a signature to a distance matrix using locality-sensitive hashing. To compare the signatures that represent merge trees, we divide them into bands, each with length r. LSH is applied to individual bands, so similar pairs are determined based on signature collision in any band. A match between merge trees requires that for at least one band, all its rows are matched. The red boxes mean 2 bands collide, where we assign the indexes of these 2 merge trees as one similar pair. We generate sim-R or sim-S as binary matrices. We mark an entry to be 1 based on the index locations of the similar pair. We then convert each similarity matrix to a distance denoted as dr or ds. Let's look at some experimental results with 2D and 3D datasets. The largest dataset contains over 5,000 merge trees. We compare the overall runtime of ds and dr when k is 20, and comparing our results against the geometric interleaving distance and the edited distance. So in terms of the efficiency, our method outperforms the interleaving distance and added distance across all datasets. For conal flow and headed flow, both ds and dr are around 10 times faster than the interleaving distance and are nearly 20 times faster than the added distance. For the viscous fingers, the interleaving distance and the added distance become intractable. So the number with asterisks are estimated based on the first few runs. The added distance will take roughly 185 days to finish the entire dataset, and our approach is estimated to be about 822 times faster than the added distance computation. Furthermore, as we dive into the runtime analysis, we separate the labeling time from the LSH comparison time. The labeling time is highlighted in bold under the dataset name. It is a one-time pre-processing step for all merge trees to generate labels. We found that the labeling process is the predominant factor in the overall runtime, especially for subpath signature, and it is indeed the bottleneck. So one of the applications of our approach is shape matching. So the LSH approaches are able to classify the majority of the shapes into the correct category, especially for subpath signatures. We use the red boxes to reflect the correct classification of each shape. For example, the shape horse and seahorse are well classified inside the category. And our LSH approaches also help to identify clusters in the heated cylinder dataset, which are highlighted as colored blocks. We select 2 time steps from each of the 3 clusters colored in orange, green, and pink to showcase the similarities within the cluster and dissimilarities outside the cluster. And please see our paper for additional results. In summary, our LSH framework is efficient and scalable in comparison with existing comparative measures for merge trees, and it can act as an alternative measure for comparing scalar fields at scale. In the future, we are interested in comparing in comparative measures for other topological descriptors using locality-sensitive hashing. And finally, we thank our funding agencies, DOE and ASF. Thank you.
You mute Ingrid.
Sorry, so I was muted. So thank you for your talk again. It was very interesting. So I will start with one question, and I was wondering how sensitive your method is with respect to wrong labeling. So I think this seems to be a very essential step in the beginning. And if you change your labeling a little bit, how much is the impact on your result?
Yeah, that's a really good question. So like, I would say it would be like very sensitive to the labelings because like all the LSH is based on like we need to have some labels for our tree nodes. Otherwise, there's like no way we can hashing vectors and we can compare merge trees. So like if we change like the label of the nodes, it would be like very sensitive like in terms of the similarity results, I would say.
Okay, thank you. There's no question on Slido, so I think we are just moving on. And thanks again. Here's a lot of applause in Discord, so people like your work.
Mhm.
Okay.
Thank you.
So then we are moving to the next talk, which is presented by Mingzhe Li, and it's about distributed augmentation, hypersweeps, and branch decompositions of contour trees for scientific exploration. Please go ahead.
To unmute myself. Sorry, did I?
You are on it.
It's weird. Hello, everyone. Can everyone hear me?
Yes.
Okay, perfect. Sorry about that. Hi, everyone. This is Mingzhe Li from the University of Utah. Today, I would like to introduce our work on distributed computation of contour trees for scientific exploration. So here is a contour map from Vancouver. The values in the map denote the height, and letters denote the locations or vertices of the underlying mesh. In this contour map, we can see peaks, saddles, and pits. In scalar field topology, they correspond to local maxima, saddles, and minima. We show an example for each type of critical points on the right. As we contract the contour lines into points, we can abstract this 2D contour map into a contour tree. The contour lines passing through the critical points will map into nodes in the tree, which we call supernodes. The rest of the contour lines will map into edges in the tree, and we call these edges superarc. A topological zone is an area where all the vertices map to the same superarc. For example, the vertices in the red zone will map to the highlighted superarc in the contour tree. We use colors to identify different topological zones. Our primary goal of visualization is to utilize the simplified contour tree for contour extraction. For example, for this contour tree of a 3D mesh, we visualize the contours surrounding the saddles. These contours demonstrate the cases where the connectivity of contours change. These contours are helpful for domain scientists to identify interesting features within the scalar field. There were previous work implementing the single-node parallel solutions to this visualization task. Besides, Carr et al. Recently introduced a distributed algorithm to compute the contour tree. However, there is still a gap to apply the distributed contour tree for visualization. And our contribution is to bridge the gap by providing distributed algorithms to compute the geometry-based importance measure, simplify the contour tree, and extract contours. In this work, we use the subtree volume size as the importance measure. The subtree volume is approximately the number of vertices within the topological zones that map to the subtree. For example, the importance of the subtree in the purple circle is 20 because there are 20 vertices in the corresponding topological zones. The way we simplify a contour tree is by doing the branch decomposition. A branch is a monotone chain of superarcs. The branch decomposition works by peeling off the less important leaf branches on the contour tree. By removing the less important leaves, we obtain a simplified contour tree and a collection of minor branches. We can ignore these minor branches when extracting contours. We follow similar ideas to the previous work introduced by Christoph et al., which simplifies the contour tree and extract contours in shared memory parallelization. First, they give an algorithm called Hypersweep to compute the subtree volume in parallel. Then, for the branch decomposition, they found that each supernode can locally decide which superarcs that it connects to are less important. They used a collection of these decisions to remove less important branches from the contour tree. For the contour extraction, they used the simplified contour tree as the query structure to see if the contour cell maps to the expected superarc. Carr et al. Recently introduced a distributed algorithm to compute the contour trees. And here is the high-level idea. We first divide the data into multiple blocks. Then, for each block, we first compute the local contour trees. Then, we swap the boundary information between each adjacent pair of top and bottom blocks and construct the part of the contour tree that goes across this boundary. Thereafter, we swap the adjacent pair of left and right. As we reduce the blocks, the underlying structure of the shared contour tree is constructed. We notice that some subtree structures are local to their blocks. For example, in the block 3 on the bottom right, the light yellow region that we highlight does not go across the boundary at all. We call the corresponding subtree structures interior forest, and the root of interior forest as attachment points. To reduce the communication cost, all the interior forests are only recorded in their local blocks. We call this data structure a distributed hierarchical contour tree, or DHCT. So here is the pipeline of our contribution to extract important contours using the DHCT. And the first step is the augmentation. The goal of the augmentation is to add attachment points in other blocks to the shared tree structure, because we notice that without the attachment points on the shared superarc, we cannot compute the subtree volume or the branch decomposition correctly. In order to share the local attachment points, we put them in an array first. For example, in block 3, we put 63, 1F, and 1B into the array. We also record the shared superarc where these attachment points locate on. We use pink nodes and arrows to indicate the involved superarcs. As we collect the attachment points from each block, we can apply the block reduction strategy. In each reduction round, we combine the attachment point arrays and sort the array by the superarc and the function value. By repeating such kind of reduction, we can eventually get an array including the attachment points from all the blocks. Now we can use this array to augment the original contour tree in block 3. In the array, 0D and 1A lying next to 0B, and 55 for A and 3 lie next to 60B, they are missing from the original block 3 contour tree. We can add these nodes into the contour tree, and then we get the augmented tree. After augmentation, we can now compute the subtree volume on the DHCT. First, we compute the volume for each superarc by counting the number of vertices locally. Then, for each block, we can compute the subtree volume using the hypersweep. To get the global subtree volume, we need to communicate and add all the local volumes of each superarc together. The communication strategy is again block reduction. It is similar to what we have used when computing the contour tree and the augmentation. We swap and add the local volume between top and bottom blocks, and then left and right. This process can be applied to most scenarios when we need to communicate the local data with other blocks. With the subtree volume as the importance measure, we can now simplify the contour tree using the branch decomposition. For the distributed branch decomposition, we first find the important superarc for each supernode in the local block. However, for a supernode, the most important superarc that it connects to may be within a different block. Therefore, we must make a communication between blocks to make sure that the importance information is correct. Lastly, we can now extract the important contours. The logic is pretty similar to the previous work. For each contour, we use the simplified contour tree as the query structure to see if the contour maps to the expected superarc. Here are some visualizations of interesting contours in some large datasets. The top right image shows the WarpX dataset from the particle accelerator simulation. The contours capture the positive and negative charge regions of the induced plasma wave shifting along the center x-axis. The bottom right is the GTOPO30 dataset describing the world elevation. The contours broadly depict the outlines of major continents and some large highlands. And on the left is the next dataset from the cosmological simulation. The contours highlight the filaments in the universe. This is the general strong scaling plot for our runtime performance. It shows the runtime as we increase the number of nodes and ranks for 3 datasets. We see that for the GTOPO30 and the WarpX dataset, the scalability is strong since the runtime keeps decreasing or reaches a minimal number as we invest more nodes for the computation. In comparison, the scalability for the next dataset is somewhat limited, as the performance does not improve much beyond a certain point. We want to highlight the performance on the WarpX dataset. We first look at the overall runtime. Using only 2 computational nodes, our implementation can already finish within 24 seconds. If we increase the number of nodes to 16, then the computation can be done in less than 5 seconds. The high performance allows us to extract contours in ad hoc visualizations. We then check the speedup of our implementation over the serial and single-node parallel implementation. The best performance of our implementation outperforms the serial implementation by more than 900 times. Even comparing against the parallel version, which already exploits 128 threads for parallelization, our algorithm can still outperform it by up to 98 times. In conclusion, we propose distributed computation on the distributed hierarchical contour tree to enable efficient contour tree simplification and important contour extraction. The improvement over the single-node parallel implementation is significant by up to 98 times. In the future, we plan to improve the scalability of our work on datasets with complex topology. We would like to thank the ASCR and ECP by US Department of Energy and NSF for supporting our work. And thanks for listening.
Thank you for your talk. Impressing what you have achieved here with a speed up. So you mentioned already for your future works that you would like to think about more complex data sets to also get a better performance. Do you already have an idea how you could approach that?
Yes, we have an idea. Right now, we try to pre-simplify the contour tree by before we completely compute the entire contour tree. Because right now, we notice that the bottleneck is the communication cost of for the attachment points. So if we can previously get rid of some interior forest, so we directly omit them and try to keep their volume somewhere else, then in that way we can reduce our communication cost and reach a better speed up.
Thank you. So there's still no question in Slido, but there's a lot of applause on Discord. And then I would like to ask you another question. And so you have been using a geometric measure as importance measure. Did you also consider to use other measures?
Right now, we focus on the volume as the measure. We also consider persistence or or hypervolume, for example. So they need non-trivial editings to our current framework, but those we believe that they are doable. But this is left for our future work.
Okay, thanks a lot for your talk.
Thank you very much.
So, and we are moving on to the next talk, a talk given by Mathieu Pont. And he will talk about Wasserstein autoencoders of merge trees and persistent diagrams. So, Mathieu, please go ahead.
I'm sorry, I think we switched order, so it should be me that should be presenting right now, not Mathieu.
in my plan, it's still the other way around. Okay, then we are going to what I have as the next talk. It's a talk by Keanu Sisouk, and he will talk about also something with Wasserstein dictionaries of persistence diagrams. Sorry for mixing this up, and go ahead.
So, hi everyone, my name is Keanu Sisouk, and I will be presenting our work on Wasserstein dictionaries of persistence diagrams. So first, what is a persistence diagram? It's an object called topological representation made of 2D points above the diagonal, usually illustrated by vertical barcodes representing the features of interest in the data and where the heights encode the importance of said features. In this example, we can see that the three mountains here are well represented in the corresponding diagram. The persistence diagram is also stable to the addition of the noise. As you can see on the right, despite the addition of the noise, we can still distinguish the three main features of interest in the diagram, and the noise is represented as points near the diagonal. Now, we will introduce a useful tool used to formally compare persistence diagrams, which is the famous Wasserstein distance defined in optimal transport. One obtains the distance by finding the optimal bijection, minimizing the sum of cos between points, here the cos being the Euclidean distance, as you can see on the left. From the distance, one can define a barycenter, namely a diagram representing a mean of an ensemble of diagrams, by finding one minimizer of this weighted sum of Wasserstein distances, where the weights are positives and summing to 1. And as you can see on the right, all the points in the barycenter colored in cyan are themselves barycenters of points of diagrams in the initial ensemble. The first paper defining a Wasserstein barycenter of persistence diagram was Turner, which we will call standard. Recent papers have developed techniques for encoding an ensemble of different topological descriptors, and we wanted to develop such method for an ensemble of persistence diagram, going beyond the descriptive power of the barycenter. And for that, we got inspired by Schmidt's work on Wasserstein dictionaries of histograms. So our contributions are the following. We introduce a simple approach for a dictionary-based encoding of an ensemble of diagrams. We show an application to data reduction and to dimensionality reduction. And we also provide an implementation in C++. So the problem is as follows. We have n input diagrams x1, xn, n barycentric weights lambda n, and in dictionary D, an ensemble of diagrams, which size m is way smaller than n. And what we want is to optimize each barycentric weights, lambda n and dictionary D, so that the nth barycenter y is a good approximation of the input diagram xn. So formally, we want to optimize this energy, which is just a sum of Wasserstein distances between each barycenter y and input diagram xn. So our method is twofold: the weights optimization and the dictionary optimization. So for the weights optimization, the method we chose is a simple gradient descent. And here is one example where we want to approximate one diagram in gray with a dictionary of 3 diagrams in blue, yellow, and green. And in this phase, we only want to optimize the weights, not the dictionary. The cyan diagram is the barycenter of the dictionary initialized with vector weights 1/3, 1/3, 1/3. And the arrows represent the direction each sign point should take. And we retrieve those using the optimal bijection from the Wasserstein distance between the gray diagram and the cyan one. Then we compute a gradient and we update. And as you can see on the right, each cyan point moved to be a better approximation of its assigned gray one without modifying any elements in the dictionary. And for the math, please see the paper. Now for the dictionary optimization, it's the same thing. Here we only want to optimize the dictionary, not the vector weights, and let it be to be equal 1/3, 1/3, and 1/3. The arrows represent the direction each points in the elements in the dictionary should take, and we retrieve those using the optimal bijection between the gray diagram and the sign 1, and the optimal bijections between the barycenter and each element in the dictionary. We compute a gradient, and then we update. And as you can see on the right, each points in the diagrams in the dictionary moved so that each sign point is a better approximation of its assigned gray one. And again, for the math, please see the paper. Regarding our running time results, on 12 different datasets issued by VIS and on previous work, our method has a computational time of at most 10 minutes on 20 cores, which we consider to be an acceptable preprocessing time prior to an interactive exploration. Our work can firstly be applied for a data reduction problematic. Here is a visual comparison between 3 diagrams taken from a dataset of 12 composed of 3 clusters of 4 members each. So one diagram representing one cluster, and their approximations generated by our method after optimizing the weights and the dictionary. We see the 3 original scalar fields and their corresponding diagram on the top right of each field. The color spheres represent the features of interest, and one can visually notice that the set features are well represented in the approximations. And notably for this example, this frame quantity represents the total size of our elements in the dictionary, and we limited it to be equal to 1/5 the total size of our initial ensemble. So overall, we have a compression factor of about 5. The second application is dimensionality reduction. If we limit ourselves to have only 3 elements in our dictionary, using the 3 Wasserstein distances between them and the law of cosines, one can define a 2D triangle, then use the barycentric weights as 2D barycentric coefficients, and generate 2D barycenters. Here we have a planar layout of 3. Here we have a visual comparison of 3 planar layouts issued by 2 classical methods, MDS and TSNE, and our method on the right. And we have seen across 12 different datasets that our method is a compromise of the 2 classical methods regarding 3 different scores. As a conclusion, we propose a dictionary method for persistence diagrams that is simple. We also introduced a persistence-driven multiscaling approach, which elevates this initial method. And again, for more details, please see the paper. We also propose a method with applications in data reduction and in dimensionality reduction. And as for the perspectives, one may exploit the encoding in other applications, such as maybe using the barycentric weights as input in neural networks, or maybe generalizing our method to other topological representations. Also, we provide the original code source, which was replicability stamped to replicate the experimental results. So thank you very much for listening, and I will gladly answer any questions.
Thank you very much for your talk. I already have a question here, and it's from Wang, asking, would you please clarify the difference between the atom optimization and the weight optimization?
The difference between the weights optimization and the atoms optimization, you mean in the concept or just what I am optimizing? Because for both optimization, I'm using a gradient descent. So the concept is basically the same. We are using the optimal bijection between each diagram to retrieve the information, and then we compute a gradient. The difference between the weights optimization and the elements in the dictionary is that for the dictionary, we optimize literally the points needed to build a barycenter, whereas the optimizing the barycentric weights is just optimizing the barycentric coefficients needed. So I hope I've answered your question, but
Thank you. There's another question asking how stable is your method in regards to outliers?
yes, that is a good question. It is quite sensible. I have some slides here. Basically, we have seen an example where we have one outliers in a data set of 12 here, as you can see in the distance matrix. And what we have seen is that when we use our initialization method to initialize the dictionary, the approximation was not of a good quality. So the method we would preconize is to maybe use one element of the dictionary for this outlier, basically.
Okay, thank you. I have a follow-up question, and this concerns the definition of the dictionary in the first place. I guess that the number of atoms is very small for your entire. So how do you estimate a good number of atoms?
So basically, it's quite empirical. We don't have a formal answer for that. The empirical choice we have chosen is to take, if we have an ensemble of diagrams, if we know the number of clusters beforehand, the ground truth of number of clusters, we just choose the size of the dictionary to be equal to the number of clusters in the dataset.
Okay. I guess we have to move on. I still have a lot of questions. Maybe I will ask in another time. Good.
Okay.
Thanks a lot. And I hope that now I'm right when I introduce Martin to the next talk, giving to talk about Wasserstein auto-encoders of merge-tree synthesis. So Martin, please go ahead.
All right, thank you. So hello everyone, my name is Mathieu Pont and today I will present this joint work done with Julien Thierny, where we are interested in the analysis and visualization of ensembles of scientific data. However, their size and complexity are constantly increasing and can challenge their analysis. And this fact has motivated the use of topological methods to summarize the data in concise and informative representations that allow to extract the important structures within the data and that allow memory storage order magnitude lower than the data themselves. And the strategy consists then in analyzing this ensemble of data based on the corresponding ensemble of topological representations. So many methods have been proposed for this, to compare them, for instance, or to estimate the average of such ensembles, or to better understand its variability. However, all the methods that were proposed to analyze the variability in such ensembles can only focus on linear and simple trends of variability. So in this work, we wanted to go beyond what was proposed before in order to detect more complicated and non-linear trends of variability in an ensemble of topological representations. So for this, we take inspiration of a method called the Auto-Encoder that can extract such patterns of variability for point cloud, and we adapt it to make it able to process topological representations. So we define a theoretical formalism and an efficient algorithm to use this method in practice, and we provide an implementation and some applications. So in this work, we focus on scalar fit, the function defined on the domain. Here we have an example that can be seen as a 2D image, and where we have used the third dimension to represent the function value. And we can see 4 peaks of value that can be encoded in a representation called the Pestens diagram. So it is a set of points where each point corresponds to a structure or peak of value inside the data, and we call this a Pestens pair. And in this work, we visually represent each Pestens pair with a bar whose height corresponds to the height and function value of the corresponding structure in the domain. And we can define another representation called the merge tree that additionally indicates how the structures are connected together in the domain thanks to the tree hierarchy. And everything that I will explain will work for both merge trees and Pestens diagrams. So we can then use the Pestens diagrams of 2 scalar fits to compare them using the Wasserstein distance from optimal transports that will assign for each point of the first diagram a point in the second one. Each assignment has a cost, and we want to find a bijective map having the lowest total cost. We have a similar distance for merge trees that exploit the structure of the trees when we make these assignments. So now we first summarize the autoencoder method in the Euclidean setting and then explain how we can adapt this method to manipulate topological representations. So an autoencoder is a kind of neural network architecture that consists in a sequence of layers. Each layer applies a linear transformation to an input point cloud, possibly changing the dimension, followed by a translation that we don't show in this figure. And then a nonlinear function is applied, such as the popular Rübel function that will intuitively crop to zero all the negative coordinate values. And an interesting intuition that will help us later to adapt this to topological representations is that we can define this linear transformation as a projection of the point cloud on a basis in the original space, where we want to find the coordinates of a point in this basis that minimize the distance to an input point. Now we can define the autoencoder as a sequence of layers that will first reduce the dimensionality of the input point cloud in what is called the latent space, and then we'll get back to the original space. The goal is to reconstruct the input point cloud at the output of the network by optimizing the parameters of each layer in order to minimize the reconstruction error. And the latent space here acts as a bottleneck that forces the autoencoder to maintain a pertinent representation of the point cloud allowing its good reconstruction. And now we want to adapt this method to topological representations. For this, we need to redefine all these geometric tools of basis, projection, and so on from the Euclidean space to the Wasserstein space of topological representations. So given a persistent diagram, we can define the axis of a basis as a set of vectors that will move each point in a direction. We can define another axis in the same manner. These two axes, these two sets of vectors can be used to define a basis in the Wasserstein space. And given some coordinates, we can express a new diagram in this basis. We can now define a layer to process topological representations. And as in the Euclidean setting, we'll define this as a projection on a basis, but here in the Wasserstein space. We want to find the coordinates of a diagram in this basis that minimize its distance to an input diagram. However, doing a projection in the space of topological representations is not as simple as in the Euclidean space, and we propose an iterative method to approximate this in practice, and the details are in the paper. Then, as in the Euclidean setting, we can apply a nonlinear function on these coordinates, and to get a new persistence diagram at the output of the layer, we can use the coordinate that we have just found in another basis that will also be optimized. Now we can use many layers to create what we call a Wasserstein autoencoder that process merge trees of persistence diagrams from end to end. So let's say we have an ensemble of scalar fields. We can compute the persistence diagram and visualize all the persistence pairs in an overlapped view. And here, each diagram has two points, and the points having the same color belong to the same diagram. And we see here that there are nonlinear circular patterns. Now we can pass the diagrams through the network that will progressively unwrap the nonlinear structures until arriving in the latent space. And if we move along this one-dimensional axis in the latent space, it will correspond to a nonlinear displacement in the original space following the circle shape, and allowing to effectively capture a nonlinear pattern. And then we can reconstruct the diagrams by wrapping again the nonlinear structures, and the goal here is to minimize the reconstruction error, the Wasserstein distance between an input topological representation and its reconstruction at the output of the network. And we propose a method using gradient descent to do this. And what I've just shown here is a concrete example that was computed with our method. So we evaluated our method over different ensemble of data, having dozens of members per ensemble in average, and from dozen to 1,000 persistence pairs or structures in average in each topological representation. And the computation time of our method is in the order of minutes, varying from few seconds to few hours for the biggest examples. Now we have a first application where the goal is to compress an ensemble of topological representations by keeping only the last layer of the network and the coordinates of each representation in this layer, allowing its reconstruction. And now we want to know how good this reconstruction is, for instance, by trying to reproduce some analysis tasks with these reconstructions, that we could have done with the original representations. And here we reproduce a feature tracking between the time steps of a time-varying dataset using the assignments between the reconstructed merge trees, validating the relevance of this compression. And with the same compression factor, we can have a lower reconstruction error with our method compared to a linear method of the literature. Next, we have dimensionality reduction, where we use the coordinates of the topological representations in the latent space as coordinates on the 2D plane. And we evaluate this with indicators that tell us how much the clusters are well preserved compared to the original space, and the sim indicator that tells us how much we have well preserved the distances. We compare our method with popular ones of the literature, and this table averages these indicators over all the ensembles. Moreover, we propose variants of our method by adding penalty terms in the optimization. The details of this are in the paper, but briefly we have a penalty term that will help the optimization to better preserve the distances. We have another one that will help to better preserve the clusters, and we can use both at the same time. When doing so, we reach a trade-off that provides the best results over existing methods. And finally, our network processes topological descriptors from end to end, therefore we can observe how they are transformed throughout the network. So here we have a time-varying dataset that corresponds to a hurricane, and there are mainly 3 phases, and we are shown one number per phase. We have the corresponding Pestens diagram, the reconstructed ones, and we can look at the 2D layout from the latent space. And we can see that the method recovers the temporal nature of the ensemble, where each point that corresponds to a Pestens diagram is colored by its phase, and the phases are correctly ordered given time. Now we can look at the overlapped view of all the Pestens pairs of the inputs, and when we zoom on them, we see complicated and mixed up patterns. And when we look at the same overlapped view but for the pairs of the diagrams in the latent space, we see that the model unwraps these complicated patterns by linearizing them and by recovering the temporal nature of the ensemble on a feature level. So to conclude, we have proposed a method to analyze the structure's variability in an ensemble of data described by their topological representations. Our method, called Wasserstein Auto-Encoder, allows to extract nonlinear patterns of variability in merge trees and Pestens diagrams, and there are shown applications in dimensional reduction and compression. Our paper has been certified replicable by the Replicability Stamp initiative. And finally, in terms of perspective, we could adapt this method to more advanced topological representations, such as contour trees or grid graphs, or use the layer that we have proposed in other optimization programs. So this is the end of my talk, and we can now move to the question, and thank you.
Thank you very much for this interesting talk. I don't see any questions yet. So I would start with one question. So maybe you said it, but I didn't really understand how you reconstruct merge trees. So I think when you are having your reconstruction of the distance diagram, but how do you recover kind of the connectivity of the merge tree afterwards?
Yeah, sure. So the idea is that when we define a basis for a layer in our model, the merge tree structure will not change. So it means, for instance, here we have the vectors that move each Pestens pair of a diagram in a direction. We'll have kind of the same for merge trees, but the structure will stay the same when we move the Pestens pairs in the birthday space. So basically, we have a fixed structure for each basis, for each layer on our network.
Thank you. So there are still no questions here. There are the applause as before. Julian says great talk, and but I think then we move on to the next talk.
Sure. Thank you.
So now we're coming to the last talk of the session, and this talk will be given by Adil Zafar, and it's about topological separation of vortices. Please go ahead.
Hi, are you able to see my screen and hear me properly?
Yes.
Just give me a second. Hi, everyone. My name is Adil Zafar. I'm a third-year PhD student at Computer Science Department of University of Houston. So in this presentation, I'm going to talk about topological separation of vortices. And this project is funded by National Science Foundation, OSC 2102761. Before I move on, I would like to mention that this work is more towards the application of TDA rather than being on the theory or the techniques of TDA. So this will be the agenda of my presentation. I'll start my presentation with the introduction, following with the previous work. Then I'll focus on our methodology that consists of two parts, topological separation and avoiding inaccurate split. Then I'll share the results of our method and ending my presentation with the concluding remarks. So vortices are one of the most crucial components for the study of fluid flows. They have complex configurations and they undergo complex interaction, especially in turbulent flows. Region-based methods such as Q, lambda2, delta, lambda CA, etc., are usually used to extract vortices in fluid flows, but these methods are threshold sensitive and they can affect the shape, sizes, and extent of the extracted vortices. A single extracted region based on a certain threshold could result in multiple intertwined vortices. These vortices first need to be separated from each other in order to compute individual vortex statistics. So in this work, we present a vortex separation method that extends the contour tree-based segmentation method. So in the first step, we get the segmentation based on the region's contour tree. And then we use a subsequent step called layering to separate a region into exactly two vortices. And this is the recursive process. However, traditional contour tree segmentation could result in a large number of regions due to having many scalar field critical points. Therefore, to avoid inaccurate splitting, we use something called as vorticity lines to compute a parameter that decides whether a region should split further. Our results demonstrate superior performance as compared to the previous method of vortex separation. In the related work, I would like to emphasize on one work that closely resembles with my work. So in that paper, the author separated individual vortices using progressive extraction of lambda2 isosurfaces. Then based on the underlying extracted isosurfaces, they assign IDs to the region cells, depending on how close they are to a certain isosurface component. This ends up in the separation of vortices. However, their method has several limitations. Firstly, they use Euclidean distance to assign IDs to the cells, which could result in a region segment having wrong IDs as highlighted in the figure B. Secondly, they use a list of lambda2 thresholds to extract isosurfaces instead of scalar field critical point, which results in the region being insufficiently covered by the isosurfaces, as shown by the red isosurface component in figure A. Lastly, due to the use of a parameter called vortex size factor, which is VSF in short, a region could result in different separations based on the value of VSF being used. Moreover, it is not straightforward to determine what value of VSF should be used to separate vortices across different datasets. Using contour tree-based segmentation, a vertical region can be separated as follows. Assume a region that has been simplified in such a way that it only contains two minima, a saddle, and a maximum. The corresponding merge tree of such a region is shown in figure B. Based on this merge tree, the corresponding segmentation is shown in C. For the understanding purposes, we call the segments associated with the minima saddle pairs the seed segments, and we call the segments associated with saddle maximum pair the Curie segments. Given the joint tree-based segmentation shown in the last slide, we use a step called layering to separate a region into exactly two vortices. I will use a 2D example for the ease of explanation. Given a joint tree-based segmentation with two seed segments and a Curie segment, we find the immediate neighboring cells of the seed segments in the Curie segments. We assign those cells the IDs of the neighboring seed segments. This assigns IDs to one layer of cells, hence called layering. By repeating this process, we end up with a region being segmented into exactly two new segments. In case of 3D vortices, the layering extends to all three dimensions, and the resultant separation of vortices is shown in figure C. The contour tree could contain a large number of critical points, and the segmentation could result in inaccurate splitting of the vortices. Therefore, after the initial segmentation and the layering process, we compute vorticity lines to check whether a vortex should split. We use the points at the boundary of the split as seeds for the vorticity lines and compute the vorticity line in both directions. Then we calculate the percentage of cells being covered by the vorticity lines in both regions, and we call those values R1 and R2. We calculate the ratio of the values R1 and R2. If the ratio is less than a certain threshold tau, we consider it an accurate split, otherwise not. The idea is that if a region belongs to one vortex, then the vorticity lines cover almost the same percentage of cells in both the regions as shown in figure C. Otherwise, they stop extending towards the second region as shown in figure B. Our method improves the following aspects of vortex separation problem as compared to the previous work. So first is adaptive splits. Our method adaptively splits by using local scalar field critical points to perform segmentation, which results in more accurate splitting. Second is avoiding inaccurate splitting. We avoid inaccurate splitting using the vorticity lines as shown in the right figure compared to the previous results as shown in the left figure that contain multiple inaccurate splits that I have highlighted in circles. Ensure sufficient splits. In the previous work, due to the use of a VSF parameter, a region could result in different splits depending on the value of VSF being used as shown by different colors in the highlighted area of figure A, B, and C. Our method is not dependent on any such parameter, which makes our results more uniform. So in the end, I'm concluding my talk with the summary of the work. So in this work, we presented a vortex separation method that extends from the control tree-based segmentation, which accurately splits the vertical regions to separate individual vortices from each other, controls the oversplitting using a statistics based on vorticity lines, is dependent upon a less sensitive parameter tau compared to the previous more sensitive parameter called VSF. However, our method still suffers from several limitations. Firstly, the integration of vorticity lines is computationally expensive. Secondly, we assume that the vorticity lines follow the shape of the vortex, which may not be true always. Lastly, if the vorticity lines integrate out of the domain prematurely, our method fails to determine the validity of split as shown in the highlighted areas of the figure. And we plan to address these limitations in the future. So these are the references I use in my presentation, and there's a lot more detail in the paper. In the end, I would like to mention that I work a lot in scientific data visualization, topological analysis, scalar or vector field topology, fluid dynamics, large-scale turbulent data analysis, and in the end, flow visualization. And I'm actively seeking for an internship. Here is a QR code to my LinkedIn profile. Feel free to reach out to have some discussion. And with that, I'm happy to take any questions. You're muted, Ingrid.
Oh, not again. So thanks for your talk. I think this is really a nice application that you have presented here.
Thank you.
You mentioned several times that that there are a lot of critical points. I would be interested kind of in the process of simplification that you have in the beginning.
Mm-hmm.
So what is kind of a good simplification to start off, or do you start with all components and go through all components?
So what we do is we extract the persistence diagram of the region. It could contain a lot of pairs of different types. So we choose the pairs with the highest persistence. One of the pairs should have maxima and minima pair, and the second pair that we should choose is the saddle minima pair. So we choose those manually with the highest persistence, and then we join them together to form the minimal merge tree that we show in our presentation. So that is the process of choosing the merge tree. And that is like we choose those pairs and then we perform the simplification based on those pairs, and we remove all other pairs, and we are just left with those two pairs that form the minimal joint tree.
This sounds like a quite tedious approach. So when looking at your images, you have hundreds of vortices, so you have to pick them all.
Yes. So that was the iterative process. By the time we submitted this paper, it was a kind of very novel approach, and that's why it was a short paper. And but since then, we have improved our technique a lot, and we are not dependent on this technique anymore. So hopefully next year, we'll have a better approach with better performance and everything.
Yeah, I'm looking forward to that.
Yeah, thank you.
Another thing I'm curious about, so you mentioned that you would like to use this for statistics. So what
Yes.
kind of statistics are you doing for these vortices?
For example, let's say you have a very huge simulation of some very high Reynolds number turbulence. So if you were like to mention, figure out how many vortices of certain type exist in a certain simulation. For example, we like one of the really important phenomena is the formation of the hairpin vortices. So if you would like to find out how many hairpin vortices are in this particular simulation, so that is the kind of statistic we are looking for. That could affect after we let's say we are able to extract those statistics, you will be able to find out what impact a certain kind of vortex can have on the overall energy dissipation of the fluid simulation. So that is our end goal.
And this means that it's quite critical, and we what you define as a correct split. And I have just a question here on Discord from Wang asking for what is the definition of an accurate split? Is
So
there a
the
physical accurate split?
actually it's very hard to define. The vortices itself, they don't have a clear definition. They are defined by different methods of vortex extraction. So in my problem, the vortex is defined by a region-based strategy, extraction strategy using scalar values, which I mentioned in my first slide, which are lambda 2q, lambda ci, and others, which are really popular. So in terms of those definitions, by accurate split, I mean a certain kind of vortex that are well known in the literature. For example, we could have stream-wise vortices and span-wise vortices, hairpin vortices, horseshoe vortices, and these other kind of vortices. So we are able to separate each kind of vortices from each other. So that is the definition of vortices I'm assuming in my work.
Okay. Thanks a lot.
Thank you.
And I think with this, we should wrap up the session. And I would like to thank all speakers again. It was really an interesting session here. And thank everybody else for attending. Bye.